Hi everyone, I'm Chris. I'm from RMIT University in Australia, and yeah, my talk's on simultaneous multi-mode analysis of SAW device temperature stability using time frequency methods. So just to break that down a bit, what we're doing is we're using these microacoustic devices called SAW devices. They're used in a wide range of sensing applications, and they usually support multiple acoustic modes going through the substrate. At the moment, when we use those devices for sensing applications in situ, we need some interface electronics to support them. And at the moment, you have to choose between having a very expensive system, which gives you all sorts of information, or going much simpler and significantly reducing the amount of data you've got to analyze. So what we want to do is, instead of using those systems, propose a new way of analyzing this using time frequency methods. So just a bit of an outline. I'll go through some background on SAW devices, how we use them for sensing, the existing techniques, why we want to do something novel, a bit on time frequency, and then the experimental setup we used to verify what we were doing. So SAW devices, they're fabricated on a piezoelectric substrate with IDTs, and the idea is you stimulate the emission of an acousto-electric wave that travels across the substrate. As it traverses the substrate, that wave can be perturbed, the velocity and attenuation, by both the mechanical properties of the substrate itself and the surrounding environment. So you can use these things for temperature sensing, pressure sensing, all sorts of stuff. But the area we're most interested in is for chemical vapor sensing. These things are very, very sensitive to small mass accumulation on the surface. So at the moment, if you build your new SAW device, you'll probably take it and plug it into a network analyzer. You set a bandwidth. It analyzes the device's frequency domain response across that bandwidth and gives you the attenuation and phase response and all that sort of stuff. But once you've done that, you would usually then take that device and implement it as a closed-loop oscillator. So just use an amplifier, really easy to set up, and the oscillation frequency of that oscillator will depend upon the SAW's frequency domain response. So both techniques have their advantages and disadvantages. VNAs give you a very complete idea of what's going on. If you've got a device that supports multiple acoustic modes, you can look in the ball at the same time. It gives you attenuation and phase measurement. But they're huge, they're really expensive, so usually they stay in the lab. You don't take them out and put them into a silo measuring something. Instead, when you go to the feedback oscillator, now you've got a much easier system to build. It's really just an amplifier and a frequency counter. But now you've reduced the amount of information you can look at. You have effectively taken your entire frequency domain response and reduced it to a single frequency. And even then, if you've got a device that has multiple modes, you may need to sit there and tune it and make it oscillate on the right one, or add filters so it doesn't jump modes. And although there are a couple of ways that this topology has been improved, it really hasn't taken off that much. So what we want to be able to do is take a SAW device with multiple modes, have an analysis system that lets us track each of those modes independently, but simultaneously, so without having to switch in and out filters. We want to do so without having to have a network analyzer there to give us this information. And the idea is to just have as much information available for analysis. We want to know if we take this device and expose it to, in this case, differing substrate temperature, how does that change the way the modes behave? So the way we're doing that is using time frequency analysis. This is a technique often used in situations where you've got time-varying spectral content signals. So here I've got just a linear FM signal. On the horizontal axis, you can see we've got time, and then on the vertical axis, we've got frequency, and we just sweep our wave through it. This shows up a lot in things like radar, biomedical, ultrasonic non-destructive testing. And the algorithm we've been using for this work is called Wigner-Ville. It's got pretty good resolution, but it's susceptible to things called cross-terms, which are these fringing effects you see on the edge. They're erroneous artifacts that are a byproduct of the math. So in order to perform time frequency analysis, we need a signal to work with. So what we did is took a fast rising edge pulse generator and effectively emulated a transient pulse going into the SAW. So it goes in one IDT, we record the signal you see on the other IDT on an oscilloscope, and then perform our transform on that signal. The idea is that this covers the operating bandwidth of the SAW device. So in order to change the way our modes were behaving, we varied substrate temperature between 30 and 150 degrees, mostly just because it's really easy to repeat and it doesn't damage the device or anything. So from that, you get a nice transient signal. So we can see we've got some like electromagnetic feed through. There's the bulk of our energy from our modes and then a few reflections. And if you take that signal and transform it to the time frequency domain, you don't get a whole lot that's useful. It's similar to like doing an FFT on it. Our original signal's bandwidth from the scope is a gigahertz. We calculate the time frequency at a discrete number of bins that you pick, and we end up with a pretty crummy resolution. So we could try and calculate more bins like you would for, say, an FFT, but this whole system is bound by the uncertainty principle. So the further you get in frequency resolution, the worse you get in temporal resolution. And even then, at the moment, we're not making very good use of the information we have available. You can see there's only like a few little areas here where there's any energy at all. So what we ended up doing was splitting that transient response signal into separate modes and then generating what I call modal TFDs for each one. And when you do that, you get this. So it's a bit hard to see, but in the bottom right, we have substrate temperature varying up and down as a function of time. And then we have 3 modes that we picked out. And you can see as substrate temperature is varied, we get some pretty significant differences going on across these 3 different modes. So our first one here is just shifting, but there's also a change in attenuation we can observe. The second one's more complicated. The shape of the energy distribution is changing. And then in the third one, we have a broadening of the energy there. So now we've got these TFDs, we need to extract something out of it to correlate to our sensing application. So the easiest thing to do is to just track that position of that peak in time and frequency. Although there's lots of other stuff you could pull out of here. So things like I mentioned, the peak shape, attenuation, assuming you calibrated the system, and probably time domain information too could easily be extracted. It's worth noting that in some of these we get some negative energy regions. These are those cross terms I mentioned. Here, they're not such a big deal because we're only dealing with like singular components, whereas before, with many components, there were all sorts of cross terms all over the place. But they don't interfere with information extraction in this case. So what we wanted to do is, if we're tracking the position of peak energy and frequency, we want to know how does this compare to the conventional methods. So we did use the same setup with both the oscillator and a VNA, and tracked the frequency of the first mode across the substrate temperature. And then we took the data that we obtained from time frequency and overlaid it too. And you can see we get pretty good agreement. So the slope is within about 5%. And from that, we can extract the temperature stability of this particular SAW device. So what we can tell from this is that the time frequency is giving us, at the very least, as much information as we've had before, and that our emulated transient pulse is giving us enough data to work with. But then, so why would you bother doing this? Well, because you get a number of other advantages. So from here, we've got substrate temperature and our frequency shift of 3 acoustic modes that were monitored simultaneously. So we did one transient pulse, which takes a couple of microseconds, transformed it, extracted the peaks, and we can overlay each of those acoustic modes on top of each other, which is something you can't do with, say, the frequency oscillator method. We did this without any sort of tuning or physical filters in the system. It's all built from sort of common lab hardware, so if you have a VNA, you've probably got a scope flying around somewhere too. And most of the processing is performed offline. So unlike if you had a VNA and you decided later you really wanted to look at a different band, here you just rebuild your digital filters, generate some more TFDs, and you can look at regions that you might not have even thought of looking before. Also, this is really easy to calculate. So on modern PCs, calculating Wignerville with the size distributions we're using happens in like less than a second. And although you're storing more data than you would have had to previously, storage is becoming really cheap, so it's not that big a deal. So just in summary, so we took Wignerville, applied it to SAW transient response. We can pick out different acoustic modes and track them all simultaneously. And the data we extracted from that shows good agreement with conventional methods while still having a few advantages over those systems. So from here, at the moment, there's no correction for the transient pulse. It's obviously not an ideal system because it's built in the real world, so there's some correction we could apply for that. There's also lots of other time frequency transforms, some of which attenuate those cross terms that we've observed. And also from those TFDs, there's potentially other metrics which I mentioned we could pull out, such as the peak shape and time domain information. And the ultimate goal of this is eventually to take SAW devices and try and separate their response mechanisms by looking at how each mode is changed in a sensing application. Thank you very much.